Hello everyone. In this lecture we will continue talking about NMR spectroscopy, and particularly here we'll discuss more about how NMR spectra is obtained and analyzed. In the earlier lecture we have seen that in basic principle of NMR spectroscopy that lies to determine local magnetic environment of nuclei, and from that we deduce the presence of neighborhood atoms from a proton, and eventually we are able to deduce chemical structure of that compound. So once you have say H1 NMR spectra, there are four important information which can be derived from that spectra. So the number one is a number of signals. For example, here we see that this is a spectra for ethanol molecule. In ethanol you have a methyl group. This methyl group is having three protons which are at equivalent position. They can be interchanged, and these three protons, they have same identical environment. So these three protons from methyl group, they give rise to single peak here. So this represents the methyl group, the proton from methyl group, this peak. Then another type of protons are in CH2 group. These CH2 group protons are also at equivalent positions and they have identical environment. So you get one peak for these protons also, the separate peak. And third type of proton is the one which is bound to OH group here, OH. So you get one peak for this proton also, this from OH proton. And this OH proton peak is most downfield. That is because presence of oxygen here. And methyl group is more upfield. That's because of its most shielded one due to presence of electrons from the neighborhood carbon atoms. So the first information we acquire from NMR spectra is number of signals. So number of signals, for example, there are three peaks in the spectra of this ethyl alcohol. That simply means that indicate the number of different types of hydrogen in that molecule. So number of signal. The second is intensity of the signal. Intensity means the peak height, the peak area. So intensity of signal indicates the relative amount of each kind of hydrogen in the molecule. For example, you see from this spectra, this peak is the biggest one. It has the highest peak area, and it represents the methyl group. So 3 protons. So that is equivalent to 3 protons. Similarly, the second peak represent the proton from CH2 group, methane group, and there are 2 protons, so this is smaller peak. And likewise the third peak is the smallest one. It represents the proton, single proton from OH group. Then the third information is position of the signal. The position of the signal in NMR spectra, they are also called as chemical shift. So the position of signal indicate the type of hydrogen that molecule contain. Essentially the type of hydrogen in the sense that having the unique environment in the molecule. So for example, here there are 3 types of proton. There are 3 type proton having 3 different environment. So you have 3 signals which are positioned at different frequencies, different energy, or that's represented in ppm, that we'll discuss after this slide. So for example, the methyl group is at around 1 ppm, or the CH2 group proton between 3 to 4 ppm, and hydroxyl group proton is 5 to 6 ppm. So it represents the unique environment the proton is located. That's basically energy absorbed by that nucleus in order to resonate. Then the fourth important information is spin splitting. These peaks what we see here, they look like single, but it's not exactly not single. When we magnify them, we see that these peaks they are having split, and that splitting of the peak is because of presence of a unique hydrogen in the neighborhood. So from the peak splitting we also find out the exact number of different hydrogen in the vicinity of the peak. So that we'll discuss in the next lecture in more detail. That's called spin-spin coupling or spin-spin splitting. So spin-spin splitting give more information, more precise information about the neighboring environment of a proton. like how many protons are there in the nearby. For example, if we magnify the peak of methyl group, so this is not a single peak, we will see that it is a triplet. It will be split into 3 portions. So we'll discuss that in the next lecture in more detail. So that simply means there are 2 protons in the neighborhood of the methyl group in this molecule. This location of different peaks in NMR spectra is basically called chemical shift, and this is actually shift in the resonance frequency due to chemical environment. That's why it's called chemical shift. So here the chemical shift is the resonant frequency of an atomic nucleus relative to a standard in the magnetic field. So we always use a standard molecule here. For example, TMS, trimethylsilane, is used as standard here, so that is considered at 0 ppm. The chemical shift is considered at 0 value here, and all other frequencies absorbed by protons in the compound, they are placed relative to the TMS peak. So this is what we call chemical shift. So this chemical shift is a measure of how far the signal is from the reference compound. For example, the TMS here reference compound is 0 ppm. CH3 group in this compound, CH3CHO is the compound, so CH3 group proton is placed around 2 ppm with respect to TMS peak, and the CHO proton is around 10 ppm, that's with respect to, again with respect to the reference compound peak. And reference compound is generally used tetramethylsilane in case of H1 NMR, or trimethylsilyl propanoic acid TSP is used in case of C13 NMR. So the chemical shift is actually the relative placement of the protons frequency with respect to a reference compound. And this chemical shift is also independent of operating frequency of the spectrometer. For example, if you are measuring same compound in 300 megahertz spectrometer or 900 megahertz spectrometer, the relative positioning will be same, the ppm will be same. That is because it is in relation to the reference compound. So that's why the ppm is unique for a unique type of compound. It always remains same irrespective of what this NMR spectrometer is being used. Chemical shift is represented in parts per million in ppm, and it's represented by the symbol delta. So delta is equal to the frequency measured, the frequency absorbed by a particular nuclei divided by spectrometer frequency. So frequency absorbed by a nuclei is in hertz, whereas the spectrometer frequency is in megahertz. So that is multiplied by 10 raised to the power 6, and that's how the number we get, that's in parts per million. For example, if NMR signal, some signal is observed at frequency 300 Hz, that is higher than the signal TMS, the reference compound, and the TMS resonance frequency or the spectrometer frequency is given 300 megahertz. So in that case, the ppm of this compound, this nucleus, would be 300 Hz divided by 300 megahertz multiplied by 10 raised to the power 6. So that would be equal to 1 ppm. So this ppm is always related to the reference compound. So that's why you have fixed value irrespective of using whatever NMR spectrometer. Tetramethylsilane is very commonly used reference compound in case of H1 NMR. So this is in order to produce a value for chemical shift, TMS is used, and it's like a standard compound in NMR spectrometer. The structure is you have 4 methyl groups and they are surrounding a single silicon atom. So this works by comparing the frequency required for resonance in the observed environment with the resonant frequency of the TMS. So all the peaks, they are with respect to positioning of TMS. TMS is kept at 0 ppm here, and it's a very good compound. Why it's used as a reference compound? Because they are 12 3 into 4, there are 12 hydrogen atoms in this compound, and all these 12 hydrogen atoms, they are at equivalent positions. Equivalent position means they will give rise to a single peak. That's the first thing. Second, the silicon, carbon, hydrogen, they are not very distinct in terms of electronegativity. That's why this compound is called most shielded compound. Most shielded compound means it will require least energy. The peak would come most upfield, and that is calibrated, that is kept at 0 ppm, and all other peaks are with respect to this TMS compound. So these 12 hydrogen in TMS, they are all identical. They provide a very clear, strong signal to compare against, and is a most shielded hydrogen atom. So you get the least energy to resonate all these protons, and that's how it's kept at 0 ppm. So other peaks can be compared and they can be placed. So chemical shift spectra is generated. There are many factors which affect chemical shift in NMR. Chemical shift means, always remember, positioning of the signals, where they are positioned at what ppm value. So some of the important factors are diamagnetic shielding, presence of any electron in neighborhood of that nucleus that shift the peak, or the presence of an electronegative atom in the neighborhood that also affect the presence location of the peak. Types of hydrogen atom, primary, secondary or tertiary hydrogen, those also affect the chemical shift, the positioning of the peak. Or diamagnetic anisotropy is a property of compounds having mobile pi electrons, for example in an aromatic compound, that also influence the position of the peak or absorption of energy by the nuclei. And this is all based on shielding and deshielding effect, like we have seen in earlier lecture. If a nucleus is more shielded, it simply means the B effective would be less on that nucleus. So when B effective is less, it will absorb, nucleus will absorb less amount of radio frequency energy and in order to resonate, and the peak will be more upfield. Whereas if the nucleus is most deshielded, in that case the B effective would be high, because the most deshielded nucleus, high B effective means the nucleus will absorb high energy, high frequency of RF radiation, and the peak will be more downfield. So for example, shielding, the degree of shielding of a nucleus depends upon its surrounding electron density. For example, if you have a proton here, the peak is coming at this ppm value, but if you have some electronic cloud in vicinity, in neighborhood, in that case the peak will be shifted to more upfield direction. That is because we have seen that in earlier lecture. Also, presence of electron, they also create a magnetic field, and that magnetic field work in opposition to the applied magnetic field. That's why the effective magnetic field would be less on a shielded proton, so the peak is shifted to the upfield. Similarly, if you have an atom like Cl here, so for example you have methane group, the proton peak would be coming at this ppm. But if you have a Cl atom attached to the CH4, so it becomes CH3Cl. In that case, the chloride atom would attract electronic cloud towards itself. That's why the proton of methyl group will be more deshielded. As a result, the peak will be coming more downfield. Similarly, is another example where you have a compound like this, and in this compound, if we look at this proton, CH2 group proton, these two protons will give a single peak. If you have F in the vicinity, fluorine, which is most electronegative, the peak would coming at 4.5 ppm. Whereas if you replace this with Cl, Br or iodine atom, in that case the peak will be shifted more downfield, so it will be 3.2 ppm. So presence of electronegative atom, more electronegativity is there, it means it will be shifting more to the downfield side. Or another example could be if you have, say, CS3F, methyl fluoride. Fluorine is having maximum electronegativity, so the peak is coming at 4.26 ppm. Whereas if you have simple methane group, for example, in that case the peak would be 0.23 ppm. So it is decreasing when you are decreasing the electronegativity of a attached group in the neighborhood of this proton. Diamagnetic anisotropy is a property of compounds which have double bonds. For example, benzene ring, or you have CC double bonds. In that case, the mobile pi electrons, they produce a magnetic field, and for example, this is the direction of outside applied magnetic field, and you have benzene ring here. So pi electron in the benzene ring, they are moving, and as a result they are also producing a magnetic field in the same direction as of the applied magnetic field. So that's how the effective magnetic field on the nucleus of a hydrogen atom, for example, which is nearby, would be addition to the applied magnetic field. So actual magnetic field would be B naught plus the B local, and you have B local something. So that's why the actual magnetic field being felt by this proton would be more than the actual magnetic field being applied from the outside. It means this proton feels more magnetic field, and that also indicate that the proton would require high energy in order to resonate, because actual magnetic field applied is high, and hence the peak will be shifted to more downfield side. And this exactly happens in case of aromatic compounds. For example, you have a methyl benzene. So in methyl benzene, the methyl group protons, they are one type proton. They have a unique environment, so we call them A type, for example. Then on ortho position, these two protons, they are also unique, so they will give rise to another peak. And meta position, they are also having unique environments, so you will get a peak from these meta position protons. And the third, on the para position, which is actually at a symmetric position also, that will give rise to another peak. So you get 4 peaks from methyl benzene. And if you see the spectra, the methyl group, this proton is most shielded. They are having carbon atom nearby, so the peak will come at 2.3 ppm. So that represents the methyl group attached to the benzene ring. Whereas the B, C and D, all these protons, peak is shifted more downfield here from 6.5 to 8 ppm. And this shifting is because of the diamagnetic anisotropy that's arised due to mobile pi electron in the benzene ring, which are causing shifting of the peak to more downfield side. Type of hydrogen atoms also influence shifting. For example, as per rule, tertiary hydrogen atom shifts more than secondary than primary. So if you have a compound like this, you have a tertiary hydrogen here, and we are calling that, say, B type hydrogen. You have 2 methyl groups which are identical, so they will give rise to one type of peak, we are calling A here. Then CS2 group we are calling C, and CS3 group here, this is D. So this compound will give rise to 4 peaks. A and B, they are almost very close by, they are coming at 0.85 ppm. The C types is having a value at 1.2 ppm, whereas the B is the most downfield, around 1.5 ppm. That is because the B represents a tertiary hydrogen atom. And why it is so? Because tertiary proton is most deshielded. We can understand this from here. Tertiary hydrogen means you have at least 3 carbon in the direct vicinity. This proton is attached to one of the carbon, but in the neighborhood you have 3 carbon which are very close. And if you look at the electronegativity of carbon and hydrogen is 2.5 and 2.1. It's not very different, but there is a slight difference in the electronegativity. Carbon is slightly more electronegative. As a result, these carbon, they pull the electronic cloud towards themselves. So this proton is become deshielded. This proton is most deshielded. It lacks electronic cloud in the neighborhood because that has been pulled by the carbon atoms, and that's why deshielded proton gives a peak at most downfield. In comparison, if you see the primary hydrogen atom, in primary hydrogen you have only hydrogen in the neighborhood, only one carbon atom in the close by. So in tertiary you have more carbon in the near to this proton. That's why this peak in tertiary is most deshielded, the proton is most deshielded, and peak is more downfield. That's why the tertiary hydrogen atom peak is more on the higher frequency side. It absorbs high frequency in order to resonate in comparison to secondary and primary hydrogen atoms. Paramagnetic effect is another factor which influence the peaks. For example, paramagnetic compounds, like some atom is having free electron, so that free electron also create a magnetic field, and that magnetic field also add up in the magnetic field applied. That's why a presence of a paramagnetic atom that give rise to higher shifting of the peak towards higher energy actually, so that's called more downfield. For example, if you have a TMS in solvent in H1 NMR, you get a peak here, but if you add a paramagnetic material, the peak is shifted towards higher energy. So paramagnetic atoms also influence positioning of the chemical shift. Then multiple substituent exert a cumulative effect. For example, we see the cumulative deshielding in chloromethane. If you have CH3Cl, only single Cl atom, the peak is coming at 3.05 ppm. But if you replace hydrogen with more Cl atom, you have CHCl3, the peak will be shifted to more energy to the higher side, more downfield, that is 7.27 ppm. That is because of increasing Cl atoms, they are increasing deshielding effect to the proton here. That's why peak is being shifted more downfield. Then intermolecular interactions, they also causes more shielding and they influence the positioning of peak. For example, hydrogen bonding pattern. If you look at a methanol in solution, two methanol compounds, they interact through hydrogen bond, the OH group. And that can be compared with another compound, that's a hexafluoroacetyl acetone. The difference is that both these compounds, they have intermolecular hydrogen bonding, but if you add carbon tetrachloride, the intermolecular hydrogen bonding of hexafluoroacetyl acetone is not disrupted, whereas methanol hydrogen bonding between methanol molecules is disrupted by addition of CCl4. So you see, when CCl4 is not being added, the peaks for methanol, there are two peaks will be coming naturally because CH3, one proton from CH3, one peak from CH3, this one, and another peak from the proton to OH group. So this is the state normally when methyl groups are hydrogen bonded. Similarly, in case of this compound also, hexafluoroacetyl acetone, you get a peak here like this. But when you add carbon tetrachloride disrupt hydrogen bonding pattern of methanol. So we see as a result the methyl peak is at the same, the methyl proton peak is not shifted, but you see the OH peak, this is shifted, this has become more upfield. That represent that there was a hydrogen bond initially which has been disrupted by carbon tetrachloride, where there is no effect in this compound because CCl4 does not break intermolecular hydrogen bonding in this compound. But in case of methanol, we can clearly see after addition of CCl4 which break hydrogen bonding, the OH peak is shifted more upfield, and that is because in case of hydrogen bonding here, for example, this hydrogen bonding here, the H is present between two oxygen atoms. If the H is hydrogen bonded, so these presence of two oxygen atoms both side of H, they make it more deshielded. That's why when hydrogen bonding is present, the peak is more downfield here. If you remove hydrogen bonding, the peak will be shifted to the upfield. So now let's take some examples. For example, this is the compound where you have CC double bond, you have CH3 group one side, H, then H other side. So see how many peaks you get in NMR spectra. So you have a one proton here, we call that A type proton. Then you have another proton which is B type proton. And remember, this is a double bond here. So double bond means this position cannot rotate. So these both the proton, they will give different peak. Why? Because both have different environment. This A type has CH3 group in the vicinity, whereas the B type has this H in the vicinity. So both H having different environment, so you get different peak. We call them A type hydrogen or B type hydrogen. And because there is a double bond, so rotation is not possible. So A type and B type, they cannot interchange. That's why they are unique and give rise to different peaks. If there had been a single bond here between C and C, then this could rotate. As a result, A and B would have been giving the same peak because they would have essentially same environment. But here A and B will be different, so you'll get two peaks by A and B, then third peak by this proton, which is secondary proton, and another peak you get from CH3 because this is also having unique environments. You get four peaks from here. So naturally the secondary hydrogen atom would be most distant one at high ppm here, and then you have A and B types and D types at most upfield because that's the most shielded one. Now let's look at some more examples. The chemically equivalent protons, the proton in the same chemical environment, they give a single peak. That's we know from the earlier lecture also. So for example, if you look at this compound CH3OCHCl2, so there are two types of protons. So in NMR you will get two signals. If you look at this another compound where you have a CC double bond, you have H both sides, and you have CH3 both sides. So you get two peaks from here also because these two protons, they have the same environment. Similarly, these two methyl groups, they also have the same environment. So both the methyl group will give one peak, and these two H atoms, they will give another peak. Or if you have a compound like this one where you see you have CC double bond, one side you have H and H, other side H and Br. In this case, this is A type proton, this is B type proton. Because there is a double bond here, so they cannot rotate, so they both have the unique environment. So they will give rise to two peaks. And similarly, this is a C type proton which is having different environment. You have Br in one side and rotation is not possible, so you will get three signals from this compound. Similarly, the benzene ring. The benzene ring, we know that all these protons are at equivalent positions. So benzene ring would give a single peak in NMR spectra. But if you derivatize benzene ring with some group, for example a nitro group is added here, so as a result of addition of nitro group, you will get three signal from this compound. How? Because on ortho position you have two protons, they will give single peak together. Then on meta position you have two protons having same environment, so another peak would be by them. And you have on para position at symmetric position you have this proton which give additional peak, so you get three signal. In fact, three signal is observed when benzene ring is having any derivative group attached to it. Similarly is another example of chlorocyclobutane. This is the structure of chlorocyclobutane, and if we look at the unique hydrogen atom depending on their environment, we see that you have HA and HB. These two are unique because they have unique environment, and moreover this bond cannot rotate, so they are not at the equivalent position, they are different. So you call them HA and HB types, where one side you have Cl group, other side you have another two protons, and that's also equivalent to this kind of this HA and HB. They are same types because they have the same environment. Then these two H atoms, you call them C and D types. They are also having unique environment, and of course the proton attached to this carbon atom is E types. This also having different environment, that's more close to the Cl atom. So this chlorocyclobutane would give rise to 5 signals in NMR spectra. So the key points to remember from this lecture: the number of peak in NMR spectra equals the number of different hydrogen atom in the molecule. Electronegative atom and multiple bond in neighborhood shift peak more downfield. And the area of peak is related to the number of hydrogen atoms responsible for that signal. In fact, by integration of areas of different peaks, the relative number of hydrogen atoms also can be calculated. And peak can be splitted due to neighboring or different hydrogen. This we'll discuss in the next lecture. The splitting of peak, let's say spin-spin coupling. So you can practice how many peaks would you get in NMR spectra from these compound A, B, C, D and E. You can try to practice them, and if you have any doubt you can write in the chat box. Maybe I can help you to elucidate the number of peak you would get from these compounds in H1 NMR spectra.